Hey guys, welcome back to part 2 on our discussion about gas laws. So today we're just going to talk about 3 different gas laws: the ideal gas law, Dalton's law, and Graham's law. So here's the first gas law we'll talk about today. This is the ideal gas law. It's simply this formula right here, PV equals nRT. This is one of the most used of all the gas laws. I still remember this formula from when I was in high school. PV equals nRT. P is pressure, of course, like always. Here are the units for pressure. Volume. Volume in this case must be in liters. Absolutely has to be in liters. The other gas laws you could have gotten away with doing milliliters, but when we're doing ideal gas law problems, we have to have liters. N is moles. Moles, we're using moles this time. There's no other moles other than in the ideal gas law. R is the ideal gas law constant. So it just depends on whatever your pressure is. Just plug in these numbers down here for R. If your pressure is in kPa, make sure R is 8.31. If you're doing ATM, atmospheres, make sure R is 0.082. These are really the only two that we're going to do. If we do millimeters of mercury or torr, we would have to look up a different R value, but we're going to stick to these two. And again, as always with gas laws, temperature must be in Kelvin. All right, before we move on to any heavy-duty calculations, I have to introduce you to something called STP. STP stands for Standard Temperature and Pressure. Scientists will often report experiments done at STP, and all it is these specific numbers. Standard temperature is 273 K. This is 0 degrees Celsius. So like right about freezing is your standard temperature for gas problems. So we're going to just use 273. For pressure, depending on which unit you're going to use, standard pressure is going to be 101.3 if we're talking about kPa, or 1 atmosphere, 760 millimeters of mercury, or 760 torr. These are all equivalent, just like Fahrenheit and Celsius. It's just different units. So we're going to use these values for standard pressure depending on the formula. R, as I mentioned before, is the ideal gas constant. So let's see where this number comes from. Let's say we have 1 mole of a gas at STP, at standard temperature and pressure. So we can plug in these numbers. Let's do it in kPa. So our pressure is 101.3. The volume, remember 1 mole is 22.4 liters, right? Remember that? There we go. 1 mole. Let's solve for R. Standard temperature is 273. You do the math here, and you're going to come out with 8.31. If we did this for atmospheres, this would be a 1 over here, and we would get the other R value, which would be 0.821. So it just depends on the unit for pressure that you use over here. All right, so let's get to a regular run-of-the-mill ideal gas law problem. All right, so here's our formula. Here's our question. What is the volume? We're looking for volume here. If we have 0.59 moles of a gas, a pressure of 250 kPa, and a temperature of 30 Celsius. All right, so we're just going to plug in numbers to our formula. One of the ways you'll recognize an ideal gas law problem is if you see the word moles, because this is the only formula that deals with moles. So right away, when you see moles, you should be thinking PV equals nRT. So let's just plug in the numbers that we're given here. What is the volume? So we're looking for volume of 0.59 moles. N is moles, so put the 0.59 there. We have a pressure of 250 kPa. Here's pressure. Okay. R, because this is kPa, R is going to be 8.31. And temperature is 30 C. Remember, we always have to have these numbers in Kelvin, so we're going to add 273. So that becomes 303 Kelvin. This is where people make mistakes here with gas law problems. They forget to convert it into Kelvin. You got to do it straight away. You can't do it. You can't plug in 30 over here and calculate it later. You got to do it right now. All right, so we're just solving for V here. So we're going to divide both sides by 250. And we get V equals, we get 5.94. And this would be in liters. Liters. Volume is always in liters when we're talking about the ideal gas law. All right, so pretty simple. We're just plugging numbers in here and solving for whatever is missing. Okay, let's try another one. What is the volume of a balloon if it contains 10 moles of helium at STP? All right, so we have our ideal gas law problem. I know it's an ideal gas law because I see moles in there. Okay, again, we're solving for volume. Says what is the volume? It contains 10 moles of helium at STP. So standard temperature is 273. So that's T. Just going to plug that in. When it says STP, you just plug in this STP numbers. For pressure, because I'm not giving any other information here, I can do this in kPa or ATM. Let's just do it in ATM. So standard pressure for ATM is 1. I'll make things a little easier. But now because we're doing ATM, R is going to be 0.082. Okay, so we solve for V. And we come up with 224, divided by 1, it's the same number. So there we go. So 10 moles of helium under these conditions, STP conditions, it's going to be 224 liters. All right, just plug in numbers in. Let's try one that's a little trickier. This time it says we have 500 grams of something. So hopefully you're thinking about your favorite formula. Grams equals molar mass times moles. All right, there's no grams inside the ideal gas law formula, but we can go from grams to moles and then plug that into there. So let's see what else we got here. We have PV equals nRT. Let's plug in what we have. What is the pressure? So we're looking for pressure of a balloon that contains 500 grams. We'll get to that in a second. A volume of 14 liters. And a temperature of 300 K. It's in K, so we leave it alone. 300 is our temperature. Our pressure, what is the pressure? So we're not given a unit for pressure, so we can use whatever we want. So it depends on what you're going to set R for. Let's set R for 8.31, which means our formula, our pressure, our answer is going to be in kPa. So it doesn't say what unit of pressure. So I'm just going to pick kPa. I'll use 8.31. If you did 0.082, your answer would have just been an ATM. So now moles, we have moles and we have two unknowns here. We can't solve this if that's the case, but because we have 500 grams, we're going to go 500 grams equals the molar mass of helium, which is 4 times moles. Solve for moles, divide by 4. We come up with 125 moles. Okay, now we can plug that in over here, 125. And now we can solve for pressure. So we're going to divide both sides by 14. P equals 125 times 8.31 times 300 divided by 14. This comes out to 22,259. And we did our pressure. We did our R is 8.31, so that's kPa. There's our answer. 22,259. We have a lot of helium inside a small spot in a small balloon, so we're going to get a pretty high pressure. All right, so when you see grams, you got to be thinking grams and moles are always related, and we're going to use the ideal gas law. Let's try another one. Here's a different variation of the same kind of thing. How many grams, this time we're solving for grams of nitrogen gas or in a giant hot air balloon that has a pressure of 3.5 atm, a volume of 2 million liters, and a temperature of 393 Kelvin. So this is a hot air balloon. I actually looked it up. This is about how much volume is in a hot air balloon, 2 million liters. That's kind of a lot. So let's see what we got here. PV equals nRT. We have how many grams? We're looking for grams. So this is probably going to have to do with the moles. Again, we're going to be using this somewhere along the line. We'll just write that down to keep track of it because where it says how many grams. We have a pressure of 3.5 atm. There's our pressure. Has a volume of 2 million. I'll just do 2 times 10 to the 6 just to save space. We're solving for moles, hopefully, right? Let's see how we go here. R, this is an atm, so R is going to be 0.082. And then our temperature is in Kelvin, 393. Okay, so you see we can solve for moles, and then we're going to take moles and plug it in over here and use the molar mass. Nitrogen gas, the molar nitrogen gas is N2. Remember, nitrogen is one of the diatomic 7, so we're going to have to realize the molar mass of this is going to be 14 times 2, which is 28. All right, let's finish up this over here before we do this. 3.5 times 2 million, 7 million equals N 32.23. Okay, divide by 32.23 on both sides. Moles comes out to 217,189 moles. That's a lot of moles. Well, we're talking about a giant hot air balloon. So we're going to plug that in over here. 217,189 times 28. And we come up with a huge number. So we come up with about 6 million grams of nitrogen. So there's about 6 million grams of nitrogen in this giant hot air balloon. Okay, here's another gas law. This is called Dalton's Law of partial pressure. This has to do with the pressures, the partial pressures of a gas in some container. So, let's say we have some container. I mean, say we have like the cylinder. You've seen cylinders before, gas cylinders, and they have little valves on them, right? Let's say inside this tank, there's a total of 500 kPa. That's the total. It consists of 3 different gases. Let's say gas number 1 has 100 kPa. Gas number 2 has 200 kPa. What do you suppose gas number 3 would have? This has to add up all to 500. So we have 300. The last one would be 200. 2, 4, 500. If you add up all the parts, you get a total. Very simple. That's all Dalton's Law is about. So let's say we have a container of air with a total pressure of 102 kPa. It contains 78.1 kPa of nitrogen plus 20.9 kPa of oxygen plus some argon. What is the pressure of the argon? So all we're doing is taking the 102, subtracting 78.1, subtracting 20.9, and for the argon, we get 3 kPa. Okay, pretty simple. The parts add up to the whole. The final law is called Graham's Law. This one is about how fast gases move. If you remember back to the very first slide of the first video, I was talking about kinetic molecular theory. One of the postulates there said that small particles move faster than larger ones. So that's what this is about. This relates to molar mass of two different things and the rate on how fast they go. So we'll do a calculation there in a second. But first, we have to think about two new vocabulary words. Effusion refers to the movement of gas particles through a small hole or porous membrane. Think of a balloon. Think of a balloon. What is one of the reasons why you have a helium balloon and in a week or so the balloon is dead? It's not floating anymore. Most of the helium came out of it. That's because the helium came out through the small pores of the balloon. The latex in a balloon is somewhat porous, so things are going to escape out of there. So let me ask you this. If you have a helium balloon, which has pretty small particles, or let's say you had an argon balloon, which is a little bit larger, which do you think would stay in the balloon longer? The one with the larger particles is not going to seep out as quickly. Argon is bigger than helium. The argon is going to stay in the balloon longer than helium would. Okay, so this just refers to the movement through a membrane. Diffusion is the process of a substance spreading out evenly to fill its container or its environment. I have a perfume bottle over here. Let's imagine we open the perfume bottle up in our classroom. It's going to take a little bit of time for that smell to spread out throughout the entire room. It'll depend on the air conditioning. If the air conditioning is running and blowing the air around, or if it's just diffusing by itself, it's going to take a while to get to the other side of the room. So that's diffusion, just spreading out evenly to fill a container. So Graham's law is about how fast these gases can move, either by effusion or diffusion. So here's a typical calculation with Graham's law. Let's get our formula here. So the rate of A over B equals the square root of the molar mass of B over A. Okay, where A is going to be our smaller molecule, because the smaller one's going to move faster, so you want to have that as a ratio to the slower one. All right, so first of all, which will diffuse fastest? Neon or xenon? Which one is smaller? You got to look at the molar masses of these. You realize neon is smaller than xenon. The molar mass of neon is 20. The molar mass of xenon is 131. So clearly neon is faster. So which is going to move faster? Neon is going to move faster. How much faster is it going to move? This is where this calculation comes about. So all you have to do is you take the molar masses. Now remember, you want to put the larger one on top. Notice how this is the molar mass of B, which is the one on the bottom here. So it's the opposite. Be careful there. So we're going to put the larger one on top, 131. Molar mass of your smaller one's up top. And you're going to do the square root of this. So do 131 divided by 20. You're going to get 6.55. And then do the square root of 6.55, which comes out to 2.56. So this says xenon is faster by 2.56 times. It's 2.5 times faster than xenon. Big difference. Much faster.